You open a mobile app, drop a location pin, and almost instantly, thousands of nearby data points radiate outward across the map. This localized discovery mechanic is the core computational engine behind platforms like Yelp, TripAdvisor, and Uber. The core functional requirement is clear. The system takes your exact GPS coordinates and a search radius and returns a ranked list of relevant locations. To accomplish this globally, the infrastructure has to index over 400 million static points of interest. It must execute the search, sort the geographic data, and return the results in under 200 milliseconds. At peak load, the system has to handle up to 100,000 of these queries every single second without failing. Hitting these metrics requires moving beyond standard databases to solve a mathematical bottleneck called dimensionality reduction. Traditional relational databases and their B-tree indexes are highly optimized for searching one-dimensional, sortable data like alphabetical names or timestamps. Geographic coordinates break that indexing logic because they rely on two completely independent dimensions, latitude and longitude. Look at this standard SQL table. If you write a query attempting to draw a bounding box using between statements for latitude and longitude, you get crossed search paths. The database engine cannot efficiently intersect two separate B-tree indexes, retrieving massive amounts of irrelevant rows. To resolve this, the database is inevitably forced to bypass the indexes and trigger a full table scan. Running a full table scan across 400 million rows for every single user request results in an immediate performance collapse. The solution is spatial indexing. This is the process of mathematically mapping two-dimensional space into a one-dimensional format that a database can actually search. Raw SQL is incompatible with low-latency geographic searches. Engineers have to architect entirely new algorithmic data structures. One method is the Geohash algorithm. It's a fixed grid string encoding system that recursively divides the globe into smaller binary grids. It starts by splitting the latitude range in half. If your target falls lower, it assigns a 0. The upper gets a 1. It then performs the exact same binary bisection for the longitude range. The algorithm interleaves these latitude and longitude bits together to form a single continuous binary string. That long binary sequence is then compressed using base 32 encoding into a short alphanumeric code. This creates what is known as the prefix property. Locations that are geographically close to each other will share a long identical string prefix. This transforms an expensive two-dimensional spatial search into a hyper-fast one-dimensional string prefix match inside the database. However, this fixed grid creates a critical edge case known as the boundary problem. Notice how these two dots are placed mere millimeters apart on the map, yet they generate completely different geohash strings. Users could sit next to each other, but if separated by a major boundary line, like the equator, their hashes share no common prefix. To engineer around this, a query must always fetch the target cell plus all 8 surrounding neighboring cells. That neighbor fetching process is handled by the application code, not the database itself. Geohash solves the two-dimensional problem with incredible string matching speed, but its rigid grid introduces boundary risks that the application layer must manually mitigate. A fixed grid system like Geohash has an inherent flaw. It cannot adapt to the massive variance in real-world population density. In an urban environment, a single square mile can contain tens of thousands of indexable locations. Contrast that with a rural area, where an identically sized geographic grid might contain only a single point of interest. To solve this, engineers use the QuadTree. It's an in-memory data structure that abandons fixed grids for density-adaptive partitioning. The splitting rule is simple. A quadrant only subdivides into 4 children when the number of locations inside it hits a predefined bucket limit. As a result, a dense city fractures into hundreds of deep, tiny quadrants, while a rural state remains a single massive block. When a search executes, the system traces the user's coordinates down from the root node to the specific leaf node containing their location. This creates a perfectly balanced search depth, operating in logarithmic time regardless of geographic density. There is a trade-off. Unlike Geohash strings, a QuadTree requires significant memory overhead to store all internal nodes and child pointers. It also introduces computational complexity, requiring the system to constantly rebalance the tree if locations frequently move or change. The QuadTree elegantly solves the density problem by dynamically adjusting its own resolution, trading the simplicity of a string for a memory-intensive, perfectly balanced tree. There is a major system design misconception here. Neither Geohash nor QuadTree actually calculates the final distance to the user. Both algorithms rely on a universal two-step pattern, starting with phase 1, index and narrow. The spatial index is used solely to instantly filter millions of global points down to a few hundred localized candidates. That brings us to phase 2, exact distance and refine. The backend runs the Haversine formula, calculating the exact geodetic distance only on that small candidate subset, filtering out false positives located in the grid corners. Every location system relies on this dual architecture to marry the logarithmic retrieval speed of a spatial index with exact geographic precision. Zooming out to the macro architecture, this flowchart shows how a user's search routes from an API gateway to a stateless location-based service, or LBS. The LBS is strictly read-heavy and stateless, allowing the engineering team to scale it horizontally during traffic spikes. A global QuadTree containing 400 million locations requires roughly 4 to 12 gigabytes of RAM. Because the index is small, it can be cached entirely in memory using a Redis cluster, bypassing slow disk reads. Meanwhile, location updates route along a separate path through a Kafka queue to a primary database, preventing them from blocking fast read queries. The algorithmic elegance of spatial indexes survives at scale because the surrounding distributed architecture isolates heavy writes and keeps the index entirely in RAM. Ultimately, choosing the right spatial algorithm depends entirely on the data velocity of the product. Geohash is highly recommended for systems with fast-moving points and high write volumes, like Uber drivers. Because geohashes are just strings, updating a moving car's location is a simple key-value update. It avoids the massive computational penalty of rebalancing a complex tree every few seconds. QuadTree excels for systems with static locations and heavy read volumes, like Yelp restaurants, where managing extreme urban density is the top priority. And when dealing with complex geographic polygons instead of single points, engineers must rely on R trees inside databases like PostGIS. System design is rarely about finding a flawless algorithm. It is about aligning the mathematical properties of a spatial index with the specific real-world constraints of your application.